solid state. The weightage of this solid state is 4 marks, that is SAQ they'll ask, or sometimes they may ask two VSAQs as a SAQ. So combined SAQ we call it as. So let us see the questions, that is VSAQs from this solid state is: define the term crystalline solid. A solid substance in which constituent particles have regular orderly arrangement is called as crystalline solid. Example for this crystalline solid is sodium chloride, potassium chloride, diamine, graphite and quartz. These are the examples for crystalline solids. Next, define the term amorphous. A solid substance in which the constituent particles do not have regular orderly arrangement is called as amorphous solids. So here the very important points are: they do not have regular orderly arrangement. Such type of solids or substances are called as amorphous solids. Examples are glass, quartz, that is quad glass, plastic, fine powder, pitch. Next, what makes a glass different from quartz? Here, the differences between quartz and glass are given. Quartz is a crystalline solid, whereas glass is a amorphous solid. Amorphous means shapeless, you can say. There is no particular shape. Such type of substances are called as amorphous solids. Whereas quartz has long range order, whereas glass has a short range order. So these are the differences between quartz and glass. Glass is considered as super cool liquid. Why? Yes, glass is considered as a super cool liquid. Reason is glass has less tendency to flow like super cooled liquid. That's why it is considered as super cold liquid. And here in the question number 5, they're asking what we call a classification, that is classify the following solids as ionic, molecular, covalent, network and amorphous solids and metallic solids. So that classification we have to identify: lithium bromide, brass, plastic, P4, graphite, ammonium phosphate, tetraphosphorus decoxide, silicon, rubidium, iodine, SiC, carborundum will say. So in these compounds, lithium bromide is ionic solid. And next, ammonium phosphate also ionic solid. Next, brass, if we consider, brass is an example for metallic solid. MS I'm writing for that. And plastic, if we consider, plastic is a amorphous solid, just now we discussed amorphous solid. Whereas coming to P4 is a molecular solid again. Next, graphite, if you consider, graphite is a covalent solid. Next, tetraphosphorus decoxide is a molecular solid. And next, coming to silicon is a covalent solid, whereas rubidium, so rubidium comes under metallic solid. Next, iodine is a molecular solid. And carborundum, that is SiC, is a covalent network. Solid. Next, how does intermolecular forces among the molecules affect the melting point? Or they may ask this question as, how does intermolecular forces among the molecules affect the melting point? As the intermolecular forces among the molecules increases, stability of a crystal increases. So simply intermolecular forces is directly proportional to stability, you can say. Intermolecular forces directly proportional to stability. As the stability of molecule increases, melting point of crystal also increases. What are X-rays are needed to probe crystal structure? Now the answer is to see the atoms. To see the atoms, we must use the light with a wavelength of 10 to the power minus 10 meters, which is possible in the X-ray region. Hence, X-rays are needed to probe the crystal structure. The ninth one is, how do you distinguish between crystal lattice and unit cell? Difference is asking. So simple, crystal lattice is nothing but it's a regular repeated 3D arrangement of the particles in the space is called as crystal lattice. Whereas coming to the unit cell is a small portion of the crystal lattice, so which is a repeated unit of lattice also you can say. Unit cell is a small portion of crystal lattice, so that is called as unit cell, which gives complete information about the crystal lattice. 10th one. How many lattice points are there in one unit cell of simple cubic lattice? So here number of lattice points is asking. So simple cube is taken here. So number of carbons are 8. 1, 2, 3, 4, 5, 6, 7, 8. So total number of corners are 8. So number of lattice points per unit cell is calculated by the formula, that is 8 into 1 by 8, that is equals to 1. Right. So 8 corner, each corner is shared by 8 other unit cells. So total number of atoms at corners is equals to 1. So here note is given, that is contribution of body centered point per unit cell is 1. Contribution of face centered point per unit cell is half. Contribution of edge centered point per unit cell is 1 by 4th. Contribution of corner point per unit cell is 1 by 8. 11th one. How many lattice points are there in one unit cell of body centered cubic lattice? So here in body centered cubic lattice, total number of atoms or rank is 2, you can say. Why? Because at corners, total number of corners 8. So we know 8 into 1 by 8, that is equals to 1. So the points, lattice points at corners of a body centered is 1, and at the same time the center of the body also one lattice point is present, so that is 1. Total how many? 2 are the lattice points. How many lattice points are there in one unit cell of face centered cubic lattice? Or they may ask the same question as, how many lattice points are there in one unit cell of face centered tetragonal lattice? So here face centered unit cell is given. So let us see. Number of corners, total number of corners, how many are there? 8 corners are present. So you can write 8 into 1 by 8, that is equals to 1. So total number of faces, corners. So now total number of faces, how many are there? 6 are there. So each face is shared by 2 another unit cells. So 2 ones are 2, 3s are 3. So these are faces. Right, faces means faces 6 are there. Each face is shared with to another unit cell. So total number of atoms, how many are there? 4. So 4 is the rank of that unit cell, you can say. So 4. Question number 14. Define the term coordination number, which is very, very important. Even the same question they'll ask in the coordination compounds also. The number of nearest neighboring particles. So these are nothing but neighboring particles of a particular unit cell is called as coordination number. So the coordination number of atoms in a simple unit cell is 6. Generally, this coordination number is calculated based on the radius ratio of cation and anion. 15th, what is the coordination number of atoms in a simple unit cell? So in the simple unit cell, coordination number is 6. 16th, what is the coordination number of atoms in a body-centered cubic structure? So in the case of body-centered cubic structure, the coordination number is 8. For example, cesium chloride, if you consider, cesium chloride coordination number is 8 because it has body-centered cubic structure. Whereas coming to sodium chloride, its coordination number is 6. It is face-centered. 17. What is the coordination number of atoms in face-centered close packed structure? So the coordination number of atoms in a face-centered close packed structure is 12. What is the coordination number of atoms in hexagonal closed pack structure? In the case of hexagonal closed pack, the coordination number is equals to 12. 19th, what is the coordination number of atoms in cubic closed pack structure? CCP will call. So here also coordination number of atoms in a cubic closed pack is 12. 20. How do you distinguish hexagonal closed pack and cubic closed packing? So here also just like differences they give. In the case of hexagonal closed pack, the layers are arranged in the pattern of AB, AB, AB. Whereas in the case of CCP, the layers are arranged in the pattern of ABC, ABC, ABC. So ABAB, ABC, ABC. That is the difference. Third layer is same as the first layer in the case of ABAB, that is in HCP, whereas the fourth layer is same as the first layer in the case of CCP. Example for HCP crystal is magnesium and zinc, whereas in the case of CCP, copper and silver. Next, this is very important question, that is Schottky defect. Schottky defect is nothing but the defect which arises when the equal number of anions and cations are missing from the lattice is called as Schottky defect. Simple, equal number of atoms are missing from the crystal, which this is called that is called as Schottky defect. So this generally, due to this defect, density of the crystal decreases. So example for this defect is sodium chloride, potassium chloride, AgBr. So here if you see the structure of this crystal, for example, here there should be B minus and here it should be A plus. Equal number of cations and anions are missing from the crystal, which leads to formation of a defect. That defect is called as Schottky defect. Next one is Frenkel defect. So this is also very important question. So here this Frenkel defect arises when the ion displaces from its normal position and occupy interstitial position, which is called as Frenkel defect. That means whatever the ion is missing from the crystal, it is occupying interstitial position in the crystal, right? That is the reason there is no change in the density remains constant. Example for that is zinc sulfide AgBr. Here one point you have to observe, AgBr is there in both the cases. So AgBr is the example for both the defects, that is Schottky defect and Frenkel defect. Why? Because in the case of Ag and Br, almost radius is the same. So when radius is same, that can be written for both the defects. Next, One more important question is F-centers. So anionic sites are occupied by unpaired electrons is called as F-centers. For example, if any anion is missing from the crystal, the position is occupied by the electron is called as F-center. So number of F-centers increases, intensity of the color increases. That point you can write here, right? Number of F-centers increases, intensity of the color of the crystal also increases. Next, question number 24, that is, what is interstitial defect? So the defect which arises when the other atoms or molecules occupy the interstitial site of the lattice is called as interstitial defect. So due to this defect, density increases. So example for this is stainless steel. Stainless steel is an example for interstitial defect. So here diagram is given. Next, gold, that is 25th question number. Gold crystallizes in a face-centered unit cell. Then what is the length of side of the unit cell? So here the atomic radius of gold atom is 0.144 nanometers. It is given in the question, atomic radius. Next, for face-centered unit cell, we have a formula that is 4r is equals to square root of 2a. From this, a is equals to 4r by root 2. So a is nothing but edge length, right? So a is equals to 4 into radius. Radius is given in the question, that is 0.144 by root 2. So I substituted the r value here so that we can get a. So a is equals to 4 into 0.14 by root 2 value is 1.414. So substituted in the formula so that we got a is equals to 0.407 nanometers. This is nanometers. 0.407 nanometers is the right edge, that is nothing but the length of side of the unit cell. So these are the some of the important questions from vsaqs of solid state.